At the end of the last video, I left you with these problems. So the first was to evaluate arctan of 0. As always, I give that a name that makes me think angle. That gives me an equation, which then allows me to rewrite it in terms of the trig function. So I can say tangent of theta equals 0, and theta must be in the appropriate interval, which is negative pi over 2 to pi over 2. Notice I need to, in order to be able to evaluate the inverse trig functions, I need to know what this interval is. I need to know the range of the inverse trig function, which corresponds to the restricted domain of the original trig function. Now, I don't just blindly memorize that. I do have it memorized, but only because I've accidentally memorized it. I always get it by sort of thinking through that process, where I'm always going to choose quadrant 1 and then an adjacent quadrant, so either 2 or 4. I need the trig function to be negative in the adjacent quadrant. And in the case of tangent, where tangent would be negative in both 2 and 4, remember we chose 4 because that gave us a connected piece of graph. Okay, excellent. Now, when I see 0, I know it's a quadrantal angle. Okay, anytime I get 0 for any trig function, it's a quadrantal angle. Need to be a little bit careful with 1 and negative 1, because for sine and cosine and secant and cosecant, we get those values at quadrantal angles, but for tangent and cotangent, we get 1 and negative 1 at angles with a reference angle of pi over 4. Okay, so let's see. This is going to be a quadrantal angle. Here's my unit circle, but between negative pi over 2 and pi over 2, we're just talking about that right half. And we're not including negative pi over 2 and pi over 2. There is only one quadrantal angle in there. Let's hope that works. This would be the point 1, 0. We'd pass through that point with the terminal ray of 0, and tangent would be 0 over 1. So that does work. So arctan of 0 is 0, the angle. This is the trig ratio. This is the angle that has that as its tangent. Okay. All right, and then we were asked to graph arctan of x. So I'm going to start with the function that we're taking the inverse of, which was our tangent with the restricted domain. So that was just one period of tangent. Notice it's kind of neat. We actually can take one full period of tangent. When we inverted sine and cosine, we had to take half of a period, because over one full period, even though it does its thing once, it repeats its y values. All right, so it was this. So this was y equals tangent of x, where x was in the interval from negative pi over 2 to pi over 2. So in inverting that, we want to turn and flip. So I did manage to remember to make a copy of that this time. So here's my graph. Rotate 90 degrees to the right, turn it, flip it top to bottom. You may or may not be able to see that, but it's kind of cool, because when we do this, we're switching the roles of x and y. So we're switching the roles of vertical and horizontal. So these vertical asymptotes, oh, I'm so sorry. I labeled those as pi and negative pi. That should have been negative pi over 2 and positive pi over 2. I left out the over 2. That is now fixed. Okay. So those vertical asymptotes at plus and minus pi over 2 become horizontal asymptotes at plus and minus pi over 2. And then the graph of tangent does something like so. So I asked for the domain and the range. Well, I can see the domain is all real numbers, so everything from negative infinity to infinity. That corresponds to the range of this function. The range, that's just this interval that we got of negative pi over 2 to positive pi over 2. That's the y values that we can get out on the graph of y equals arctan of x. And that corresponds to the restricted domain that we had over here. Excellent. And then the last thing was I asked you to describe the end behavior using arrow notation. Now we haven't done that with the previous graphs because there was no end behavior. When I looked at arc sine and arc cosine, their domains were the interval from -1 to 1. I couldn't have x going off to plus or minus infinity, but here I can. So I can say as x goes to negative infinity, so that's going to be describing the end behavior on the left, as we go off to negative infinity, arctan of x goes to -pi/2. We're approaching the y value of this asymptote. And then as x goes to positive infinity, so now we're describing the end behavior on the right side. As we go far to the right, our y values are approaching positive pi/2. So arctan of x approaches pi/2. Good stuff.